Hi there, I'm Jennifer Strong. On The Next Innovation, we feature a variety of different tech companies. We often meet with their leaders and explore how they're shaping their respective industries. And now, I want to share an exclusive interview with two of the top young leading minds in tech today. Not many of us think probably too much about space, like outer space, on a daily basis. And when we do, we probably don't think about the infrastructure that's needed to help astronauts do their jobs. Icarus Robotics wants to help change that, and they're leading an effort to develop and send out robots that can help lessen the burden of being in space. Today, I'm speaking with Chief Executive Ethan Barajas and Chief Tech Officer Jamie Palmer. They co-founded the company a couple years back with a plan to change the working landscape of space. Welcome to The Next Innovation. Hey guys, great to see you.
Good to see you as well, Jennifer.
Great to see you again.
So I've had the good fortune to get to meet you now a few different times, but for those listening who haven't met you, do you mind to start by introducing yourself?
Yeah, I'll start off really quickly. I'm Ethan, co-founder, CEO of Icarus Robotics. We'll talk about my background a bit more, but I've been lucky enough to work on a few things in the space industry and, go to some really amazing universities like Caltech and work on some space projects. And now get to work on dexterous mobile robots here at Icarus.
And I'm Jamie. I'm the other co-founder and CTO here at Icarus. My background spans a couple of different industries, from robotics research to working in robotic startups, to even a brief stint spending some time in Formula One and motorsports. So, yeah.
Okay, so how did you guys come to found a space robot company?
I think I'll kick off. For me, I got the bug early. I was lucky enough to get my first true internship at NASA when I was 17. And that was my first real engineering, you're touching something that's real internship. And it was on the autonomous growth of plants for the ISS. And I got to see what it took to build something and launch it to the actual space station. And that just stuck with me so much. And that ultimately led me to go to Caltech, where I could, stay in the JPL ecosystem. Get to work across some lunar rovers, Martian rovers, and everything the like. And that there was one key thread for me that was really interesting was, astronauts, they're really tough to get your hands on astronaut time. It's really hard. You would imagine it's a lot easier, but it's very hard. And even when we were NASA, just 5 minutes was crazy to get our experiment plugged in and run autonomously. And we saw that, the ISS is getting deorbited at the turn of the decade, and there's these commercial space stations launching. And it became an immediate question of, okay, well, what doors does this open?
Jamie, how about you? How did you come to help found a space company?
I have an unusual way of coming into, I guess, founding a space company. For me, my sort of obsession was always in and around robotics, and primarily general purpose robotics. So, starting off in university, I had done all different types of robotics research, everything from building therapeutic robots for children in hospitals to more traditional stuff like SLAM and navigation research, and then ultimately spent a lot of time at a startup called Icarus, an Irish startup, and we basically deployed autonomous UV disinfection robots to hospitals during the pandemic. Before finding myself in robotics, I was gearing up towards a career in motorsport, ended up spending a year doing test engineering at the Mercedes F1 team full time. So there I got to deal with the likes of Lewis Hamilton and George Russell, and work with a really amazing engineering team on producing the highest performance possible out of their race cars. But during this time, I missed robotics so much that I actually left. I moved to the United States. I studied in grad school in Columbia, got to work with some fantastic researchers, building things like robotic hands, and I was just grabbed by this. So my goal was to start a company, a general purpose robotics company. Myself and Ethan got picked up by a startup accelerator called Entrepreneur First, and we met and started working on the idea for Icarus together.
All right, so what is Icarus, actually? Can we back up a little bit and unpack what it is you do?
Yeah, so I think the best way to describe it in just a couple sentences is we're building these dexterous mobile general purpose robots that first help augment astronauts that are on the space station. So we're taking care of all of those routine, time consuming, even in some cases hazardous tasks that free up specialized human labor to work on really important things. And then as we go, we get to actually expand out into a scalable commercial ecosystem that encompasses not just taking out the trash, but actually manufacturing. and doing scientific experiment. And like Jamie's saying, maintaining that sort of infrastructure. A big goal for Crew 11 was to get the ISS prepped for a large upgrade of solar arrays before we deorbit. And it's one of the last large upgrades. And, we see, unfortunately, like with that health aspect, that, now that timeline is dragging. And so when we talk about putting data centers in space and all of these other massive infrastructure plans that now have what seems to be real commercial backing and steam behind them, you need that labor. And so we've been lucky enough to go ahead and partner with NASA and a pretty well-known space company, Voyager Technologies, that used to be NanoRacks. And we're prepping with them for, our first full-scale orbital deployment in the beginning of 2027, where our robot actually will be on station for full test for some of those basic menial tasks. So we're talking about cargo bag logistics, which, astronauts sometimes spend up to 14 days unpacking and repacking, just moving cargo bags that we send up every 60 days, all the way to things like basic seal inspections and filter changes. And as we gain confidence in our technology and we gain data, we can start to do some of those more tasks with finesse. So, the next 12 months are super exciting for us.
So congratulations, by the way, on your upcoming first launch. How do you prove that you're able to control, because these are still remotely controlled for now. How do you prove that you can control a robot on the space station? It's not like NASA doesn't, they take safety pretty seriously, right?
There's a couple of different aspects that you need to really think about before you put your first payload in space. So the first thing that we thought about initially was, okay, if we have a remotely operated system, do we have the dexterity that we actually need in order for this system to be feasible at all? So what we did is we built a very simple system using a lot of COTS components and actually unpacked a NASA cargo bag in real time using a real-time human operator. Then the next question that came afterwards was, okay, the space station is pretty far away. How are you going to deal with the latency? It's historically not known as having, the best latency. So we then went and actually did a test. We did plenty of sort of procedural stuff, but ultimately the biggest test that we did was 2,500 miles from our office here in New York to California. We basically had a remote robotic system and we real-time controlled it from our office and essentially did the same sort of unpacking task and some other sort of toy tasks as well. So that was the next sort of prove out of, okay, now we've injected a latency that is kind of real world, could spike and isn't just a simulated latency. And then the next sort of things that you need to do before you put your payload up there is we do a lot of testing on our safety systems, our control systems, our trajectory generation, and we do a lot of this stuff here in our office on physical hardware and in simulation. So we have a full simulation environment built of the ISS. We can then go and put the robot into zero gravity physics and actually control it with all the masses, all the inertias, everything that you would actually need, and then actually see how is this robot going to move around and act. We can simulate our sensors as well, and this is a really useful tool. Then we also pair that with some physical testing around the likes of, we have an air-bearing facility, which is a fancy way of saying, imagine a floating platform that acts almost like a hockey puck, a large hockey puck on top of a flat glass table, and we can fly our robot into the microgravity. But the biggest thing that we're really excited about is this parabolic test flight, which is coming up in the new year. So that's kind of one of the final big safety prove outs before we go. And ultimately, for anyone not familiar, it used to be called the Vomit Comet, but ultimately it's a plane that they've gutted and you fill it with experiments. And ultimately what happens is this plane goes up to an altitude and then falls, and you're falling at the same rate of gravity. And then ultimately what happens is you get essentially this free fall mimics the microgravity environment, and you get about 20 seconds of microgravity simulation, and you do this over and over and over again in these parabolas over the course of a few hours. So that's going to be our last sort of big flight prove out before we go the whole way to space.
Amazing. And just, you're right, probably most people haven't thought about this. They've probably also not thought about how far the space station is from Earth. So when you were operating between New York and California, how does that compare to operating between New York and the ISS?
So the ISS is much closer oftentimes than people think. So New York to California is approximately 2,500 miles, and the ISS to the Earth's surface is about 10 times closer. So it's about 250 miles. Now, that comes with the nuance of the communication being pinged up to a geosatellite and back down. So it's by no means free lunch. But yeah, the ISS is much closer than people think.
just to tack on there, what Jamie's saying, it's like geosat relays. They're like 22,000 miles out there. They're pretty far. So that does inject like a meaningful distance, especially when you're in station.
You talked about the vomit comet, the parabolic flight. Can you explain a bit more about what that is?
So again, what this parabolic flight is that we keep referencing is this is the idea of a plane that reaches an altitude, and essentially what this plane is doing is it's actually diving, kind of falling towards the Earth. And the really important thing is that it's falling at the same speed of gravity. So what this actually gives us is an environment inside the plane where essentially everything is floating. It's floating the exact same as microgravity. So there's been some pretty famous campaigns in the past. There's been some quite funny marketing ones. Famously, Kate Upton flew on a parabolic test flight many, many years ago, and the company got some great marketing out of that. But for us, it's less about having fun and floating in zero G, and more so about actually running some serious experiments. So what we'll be doing in those times when the plane is falling, and it'll do this a number of times over the course of an hour. So in total, we'll have a lot of time in microgravity, but we'll be running actual experiments to see, okay, our arm works under terrestrial physics. How does it work when we're in microgravity? Similarly, our base is floating around fine here in 2D, but now we have a 3D microgravity environment where we can test it. And we'll actually be running basically a full stringent test campaign where we're testing not only our subsystems, but also our full free-flying robot on this plane that consistently falls out of the sky, really climbs up to altitude and falls out of the sky again. So there's also some funny bits that you have to think about before you do that. People get nauseous. So one of the things they do is they put you on a special diet for a couple of days beforehand and suggest what you should be eating. So there's a lot of funny things operationally that we have to think about for that test too. But what I can say is everyone in the office is very much looking forward to it. It will be fun, but it is still very much an experiment.
I have never been on one of these flights. I have been in a fighter jet, and I have had my own version of a vomit comet, pulling several Gs. But I am wondering operationally too, how does this work? Because you're not going to stay in microgravity, or what the rest of us would think of as like, floating, right? So your experiment, if you're only got 20 seconds at a time of this, are you like mid-experiment, do things like fall back down? Like, how does that work?
Yeah. Exactly. So when you reach the bottom, you actually pull quite a few Gs then. So similar to probably cornering in that fighter jet you were talking about earlier. And what ultimately happens then is everything is floating for that 20 seconds, and then things are going to find their way back to a surface afterwards. At that point, then what we're doing is we're resetting anything that we want to run. Perhaps we did a trajectory with an arm. We'll probably reset that to home. Perhaps we did a trajectory with our flying base. We might reset that to a home position as well, and then prepare to run the next test item as we get into the next one. So again, yeah, we're going to be consistently reaching these low gravity environments, but also then afterwards, as we pull out of them, very high gravity environments. So we have to be prepared to essentially consistently reset our equipment throughout the flight. So you do a lot of pre-flight campaign sort of operational planning in order to account for that, because there's only certain things that you can run in that environment.
This could be completely wrong in my imagination because I haven't been in your sessions, but in my mind, I'm like, so you duck from the flying robotic arm? Does it get damaged pulling several Gs as it smacks into the bottom of the plane? Like, I don't know.
Well,
Yeah.
I think there's a lot of nice ways to deal with it. There's a lot of certain things that you can fix, certain areas. You get to design your whole experiment area. So we've seen similar experiments in the past. Have netting, have foam. There's been free-flying robots done on these flights before. So there is kind of a precedent of how do you protect your material? How do you protect your prototype? And we've seen some really great gains from other researchers, from other companies, from other agencies in the past doing similar flights and testing similar hardware. So hopefully
How do
nothing
you
should
protect
break,
your
but
colleagues from flying
touch
robots?
wood.
You just have to catch it in time. That's
Yeah.
the safety standard, is catch it in time.
So something else that I don't think we all think much about, but I do think in the year 2026, we're going to see a lot more of, is injecting intelligence into robotics. I think for most people, we probably haven't considered just how, I don't want to say dumb robots have been, but they're not AI filled. And what you're doing right now provides a lot of data that's been rather hard to get up until now. Maybe you could explain that too.
Yeah, I mean, I'll start out with the people that have actually deployed first to ISS, and I'll let Jamie run with the data question, how we're using it, how it makes our robots intelligent. The cool thing about space is we get to stand on the shoulders of giants. Everything from the Apollo era all the way to right now, this new golden era of new space and all the innovation that we're seeing coming from a few key players and everyone else piling up on that. And there's a couple of really interesting projects. The AstroV project over at NASA, which is like a free floating camera on the ISS that they've used to track astronauts and kind of film them doing experiments and test different control algorithms of movement of a mobile base. And then the other one is Japan's INTBALL from the Japanese Space Agency. And both of these are, free floating bodies, but never really any manipulation. And if you look at the robots that we have on board, a lot of them teleoperated. You look at Canadarm, we actually teleoperate this with an astronaut inside of the station to move it around, collect different things, and do different maintenance pieces on the outside of the station. And so we're lucky enough for the first time to be doing meaningful teleoperation from Earth to space, where we're doing tasks that are more than just like, for example, they did surgery, which was really interesting, but this was super small groupers that cut fake ligaments, and not really large movements, not really interacting with different sorts of payloads that aren't the one that's specifically designed for. And then for us, we get to interact with this wide range of different tasks. And that allows us to do some really special stuff at the back end.
Yeah, so the getting there with teleoperation, like Ethan said, allows us to get deployed into our environment as fast as humanly possible and allows it to essentially start providing value to these customers right away, which is super important. But the other reason why it's so important for us to get there fast is this idea of, like you touched on, data. We see across all sectors of terrestrial robots that without the correct data in distribution in the environment that you're going to be deploying in, it's very, very hard to put a robot in and do any sort of robot learning. What robot learning generally does, which is very interesting to what's been done in the past, is in the past what you have is you pre-program a robot to do an exact task. But if the lighting changes, if the thing you're manipulating changes, if anything at all meaningful changes, your robot can no longer do this task. With robot learning, what we're doing is we're putting in intelligence into these robots such that they have an understanding of what's happening around them and they can actually do very intelligent tasks. I think the biggest toy problem we're seeing people solve at the moment is robots trying to do laundry terrestrially. So you've probably seen some videos. But ultimately, this goes far past laundry, and it's much more exciting when you think about the utility that you can get out of this. But what you have to do is essentially collect this in-distribution data. So basically, the robot looks at video and it looks at its own telemetry. And then from that, it begins to learn about its environment. It learns if I do a given action, if I push something, if I pull something, if I move myself around, this is how the video changes. This is how the scene changes. So you collect what we call these action observation pairs. So your video and telemetry, and you use that to train that intelligence. So when we're teleoperated in this space station, what we can then do is collect this unique microgravity data, which is a sort of physics environment that nobody else has data on. And we can go build up the first meaningful microgravity manipulation data set for robot learning and actually train our robot to be intelligent and actually work without human operators in the future, which is exciting because it means we can go much deeper into space, things like lunar missions, things like Mars missions. But it also means that we can get much wider scale across many different tasks that would have been possible prior to that. So the whole robot learning aspect is very, very exciting for us. And we're keeping a very close eye on it.
So what's your greatest challenge right now? What is the thing that's going to, speaking of 2026, keep you busy?
Well, I think that list goes on and on and on if we're honest with it. You could have us here for the next few weeks writing that one out. But I think when you think of the core piece of what we're actually building is you're going from a company that didn't exist a year and a half ago to deploying to space in an environment with NASA within 2.5 years. And so that ramp of not only, inception of idea, going and talking to astronauts and NASA ops planners and all the commercial stakeholders and seeing, is there something that is actually buildable here? Is there something massive here? All the way to, the stage that we're at now, where we get to build these fractional prototypes with these stakeholders and with the partners that we do have, whether that be in the academic realm or the commercial realm or the government realm, and then actually deploy it that ramp is super fast. And so always controlling our scaling of the team and the scope, because as you get more team and more capability, you want to add more things on. That's like kind of the way that you look at it is you get excited about these new capabilities and say, I could do this. And then this, we call it the case of, while you're in theirs, oh, while I'm fixing this, I could go and add this and then add this. And so for us, the biggest challenge now is getting our minimal viable product actually past the safety and regulations to deploy to this environment. The integration, pulling together all of the parts and all of the people that we're working with to get our robot there and to do our deployment. But then the biggest thing becomes that engineering challenge. At the end of the day, you're solving problems that people really haven't solved before. One of the largest things that comes with a free flying robot, we talked about a couple that were just cameras that really lack manipulation, but one of the hardest problems is the problem of dynamic coupling. Mine is just building the robot, getting it there and getting it to that environment, having it actually operate the way that you want to. When your robot is a floating body, there's a fun thought experiment. You can put your arms forward and you've sufficiently shifted your mass far enough forward that your body will start to move backwards. And the best intuition people might have of this is like being in a pool. But even then, being underwater in a pool, you experience very different phenomena. And so when you're a robot and you go interact with a payload or a cargo bag, for example, and you now have this mass, it's like the dump truck problem. If I load it wrong, it tips. And so for us, we're not necessarily tipping, but that inertia really makes it hard to actually move your robot in a way that can carry out meaningful labor. Whereas you see humanoids on Earth, some are wheeled, some are legged, but they get to react against that 1G force in the Earth, and they get to move things the way that a human does. So it's a very different set of problems, just technically, of actually manipulating objects.
So I think Ethan summarized pretty well what the sort of major challenges are. But I think something I'm really excited about is we've recently done quite a bit of scaling in the engineering team. So we've brought on some people that have experience across medical robotics, autonomous machinery, and even people that have worked, at Blue Origin and Boeing on SLS and on propulsion as well. So we have, a new stock of really amazing talent to help us get there. So for me, I think the engineering is going to be pretty exciting this year.
Has anything surprised you working on all of this over the last, couple of years?
I mean, I'll kick off. I think one of the things that's most surprising once you get deep into the space industry is how invested and helpful everyone is. My exposure to the cutting edge of robotics has been initially through Jamie, and a lot of that is it's a different type of exposure than the space industry is, and it's very interesting to see both of them because we have one foot on either side of these two worlds. And when you talk about people moving things forward in the space industry and just people that shouldn't be giving you your time, like the time of day, actually saying, hey, let's meet for the next hour and let's talk about this, is something that we found has been super unique. Like one of the things that we talk about all the time that's a funny story is when we were first trying to get as much context as possible of the industry and is this even a company worth building and devoting a life's work to, we were messaging astronauts and we would get folks to actually get on with us and talk about their experiences in space for hours at a time. And I think we hit the contact me box of one of the largest commercial stations, Starlab, and now we're working with Voyager and Starlab to deploy our robot to the ISS. And so like that group, we talked to one person who I think Tim Copra was the CEO at the time. And, the very next call, we're on with him, Mike Lewis, Brad Henderson, and the entire C-suite of the operations going on there. And so that's been really, really unique. And it's also been really unique as someone that comes from the mechanical side and the space side to look at, the robotics industry and how open they are to these new sorts of applications of their technology. I think like that's one thing that's been very interesting, where people in the space industry are passionate about space and the exploration of the universe and pushing the boundaries. People in the robotics industry are the same. And if they find that really cool environment that can bring forth what they're excited about, it's this awesome marriage. And then I think the other thing that's just been really interesting has been over time, we've seen the industry evolve to you can actually do more things now than you could have in the past. And what I mean by this is NASA has this idea of flight heritage. And flight heritage, when you're at NASA, there's a big database, and this database has everything, nuts, bolts, washers, all the way to full systems that have flown to space in environment and operated correctly. When you build a new system, that's where you go, because you don't want to reclassify and go through all the safety procedures and like that you did in the past. And now when we see, SpaceX opening up so much launch for the entire community, we're seeing more things get flight heritage and that aren't just through NASA. And for us, we're using things that they couldn't have dreamed of, even on Astrobeat or some of these free-floating robots that NASA developed in the past. They have famously used boards that stopped existing in the early 2000s on some of their projects that they stopped manufacturing. Whereas we get to use the highest end, newest end, developments in the robotics world and go through our own safety processes. And so seeing that change just in the past, few years of when I was working on that autonomous plant growth lab to now has been really exciting for not only us, but the industry as a whole.
Incredible. Jamie, what about you? What surprised you?
I think a better question would be what hasn't surprised me. I think it's all been like quite a surprise so far. But yeah, I think in terms of the stuff that Ethan touched on, I think one of the biggest things for me, was definitely this idea of how forthcoming everyone is in the space industry. And it's a real privilege and pleasure to be able to work in the space industry because the people you're talking to, similarly, they love technology, they love the industry that they work in, and it's really passion driven. So, you actually have great conversations all the time. Going to a conference or something normally sounds like something that might be a little dull, but going to a conference in the space industry, you're basically spending your time with people that are much, much cooler than you, that know much more interesting things. So I've really been enjoying that and picking up everything and learning it. And I've also been sort of enjoying this idea of bringing those new sort of this new style of robotics thinking that has only really come up in the last kind of 2-3 years about the idea of general purpose robots and learning from experience, actually bringing that into the space industry and into the forefront of it as all this new infrastructure goes up. On a sort of a foundery note, I think one of the things that's been surprising is, as well as, myself and Ethan, we kind of work very closely together to try and figure out, we know what we want to build and we know what we foresee in the future, but I think neither of us could have accounted for how much time we spend storytelling. And we thought, opportunities like this is a great time to tell a story, but it happens on your everyday, when you meet a vendor, when you meet a supplier, when you're interviewing a new engineer, it's a lot of storytelling and be able to sort of articulate the thing it is that you care about and the vision that you guys see so clearly.
Yeah. I mean, of all the sectors I've covered as a journalist, I do have to say space and space tech always amaze me how collaborative it is. I mean, for competitors, boy, it seems people are so open to sharing knowledge, ideas, and just talking about what they're working on. And just it's different for me in a really beautiful way.
Well, I wanted to tack on something there to the end of what Jamie was saying about the storytelling. Um, in the beginning when we were just trying to figure out, where Icarus goes and what this actually becomes, it was a lot of that of here's our vision of the future. And very much the industry and Icarus, we've kind of sculpted that vision to be reality. And what I mean by that is right now we're at the point, even with how fast we've moved, to be able to work with these massive aerospace primes that people are familiar with, that have been around for much longer than we've been alive, to actually edit some of their infrastructure plans for these multi-billion-dollar space stations or these multi-billion-dollar operations going on in low Earth orbit. And sometimes it can be everything as simple as, oh yeah, we're going to change the way that our internal space station looks like, the actual physical design of a space station, so it can interface with your robot. And we'll put fiducials here so your robot can localize. And maybe that tab that's only meant for a human to pull, that's super small, we can actually increase the size of that tab so a robot can interact with it much easier. And so to very quickly go from, idea phase to development, doing basic tech prove outs with, some of the really amazing first people we had backing us over at NASA with the coast to coast teleoperation and them giving us, actual flight used cargo bags that have been to the ISS, to then within the year from that point, actually
editing the infrastructure of some of these massive plants, beyond just, the tabs all the way up to the entire operation of what that looks like in the future, and getting to define the entire category of what is a space robot? What does a space robot look like? When you ask most people to think about a space robot, unless they're Canadian and they think about the Canada arm on their $5 bill, they usually go to Wall-E. And so for us to actually push that forward and have the chance to make that what we're working on, and the collaborative aspect of our robot with astronauts, that's just very exciting and something that's been very cool to, see ramp so fast.
It's absolutely fascinating. Yeah, something I find really interesting in New York right now, it feels like, well, a few things going on. We're kind of coming full circle. We're watching the New York tech scene really build back up again, in a very exciting way for me, and probably for others too. I think especially post-COVID, the opportunity to work together, like where you are in the Brooklyn Navy Yard, is just a fascinating place to go walk around right now. But there's also a lot of people coming, including from Ireland, a lot of young founders. And I'm wondering what your experience of that has been, Jamie. Do you have community there?
Yeah, it's insane. I think if you wanted to be over here and only hang around with Irish people, you very much could find yourself in that bucket. But no, I think it's really amazing how many like peers that I've had from back in Ireland, whether it's been from university or different programs, that I've actually seen, found companies, and now a lot of them actually moving those companies or coming to America to found those companies as well. Really ambitious projects. There's people, companies like Interface and Solid Road that have been made really good sort of strides in the kind of more SaaS side of things, and going through YC and getting great success afterwards and raising fantastic rounds. And then even like hard tech infrastructure companies like Ulysses, building underwater robots. So I've found that over here I actually have a lot of peers and know a lot of people that have kind of come over on similar paths, sort of looking for their real you know American ambition, and kind of embedded themselves into that American venture scene, but kind of bringing that learnings, and that kind of experience that they have from growing up in Ireland, which seems to lend itself pretty well to people. Because I don't know, I think most of the people that I know that have come over to start these companies, they all seem to be doing pretty well. We all take good care of each other, and it's always nice to be able to pick up the phone, hear a friendly voice, ask or offer some advice. So I found it really great. And even, our first major investor, Finn from the GP over at Nebular, I knew Finn from back in, I think it was 2020 or 2021, where I did a program in Ireland called Patch, which was for sort of young people that were really interested in kind of pushing the frontier of science and engineering. And he mentored me in that program, and it was very much a full circle moment, sort of 4 or 5 years later, whenever he came in and kind of gave us a major investment. So yeah, I think the community is really strong. People take really good care of each other. And I think there's a lot of people to watch coming out of Ireland right now.
Very cool. Thank you both. This has been so much fun. I feel like I've learned a lot.
Oh, thank you so much. We really appreciated you having us on, and chat soon, hopefully.
Hopefully.
Thank you.
Bye, guys.
Bye.
Thanks for listening to The Next Innovation, and thank you once again to our guests, Jamie Palmer and Ethan Barajas of Icarus Robotics. This episode was produced by Situation Room Studios. Christine Barada is our executive producer, and Sharon Barrero is our senior producer. Additional production support by Global Situation Room. I'm your host, Jennifer Strong. Until next time.